2,000 years ago, Roman engineers poured concrete into the Mediterranean Sea. They didn't use rebar. They didn't use Portland cement. They didn't use industrial mixing equipment. They used volcanic ash, quicklime, and the seawater itself. Those harbours are still standing. Modern marine concrete, poured with steel reinforcement and computer-controlled curing, begins to crumble in 50 to 100 years. The Roman version is stronger today than the day it was made. This isn't legend. It's documented chemistry. MIT and Harvard confirmed it in 2023. And it's not just concrete. Modern systems are fragile by design. Heating grids fail in a single winter storm. Water pumps die the moment the power dies. Sewage plants need constant electricity just to keep a city from drowning in its own waste. The Romans engineered an empire of 1 million people that ran on gravity, fluid dynamics, and self-healing materials. No electric grid, no fossil fuel pumps, and much of what they built is still working. What follows are 15 Roman inventions, verified against research from MIT Cambridge and the writings of Vitruvius himself. By the end, you'll understand a level of engineering mastery we're still trying to reach. The number one invention is the reason a 2,000-year-old harbour wall is stronger today than the day it was poured. 4 inventions built for war. The physics inside them still shows up in modern weapon systems. Number 15. The metal-cased ball valve pump, 1st century BC. When fires broke out in the densely packed multi-story insulae blocks of ancient Rome, the empire didn't rely on motorized pressure networks. They deployed the Catacibian force pump, a twin-cylinder reciprocating piston machine built completely out of cast bronze. The true breakthrough of this apparatus wasn't just the lever-driven rocking beam, but the precision engineering of its one-way check valves. Roman craftsmen cast and precision-ground solid bronze balls, seating them perfectly into matching concave spherical sockets. When the piston was pulled upward, the vacuum lifted the ball off its seat to draw water into the chamber. On the downward stroke, hydraulic pressure instantly forced the ball back into its socket, creating a flawless metal-to-metal seal that entirely prevented backflow and forced a high-velocity stream of water out through a central directional nozzle. To achieve this, Roman engineers were machining raw metal to tolerances tight enough to hold intense hydrostatic pressure under rapid manual load. But here is the detail that proves their mastery of materials science. The alloy formula used for these pump housings was highly deliberate: 73% copper, 19% lead, and 8% tin. That specific structural ratio was engineered to eliminate galvanic corrosion, the silent electrochemical breakdown that rapidly destroys dissimilar metals when continuously exposed to water. The Romans solved galvanic corrosion nearly 2 millennia before modern chemistry even gave the phenomenon a name. Reconstructed examples prove these units reliably produced 8 to 9 pounds of continuous pressure per square inch. While lower than today's hyper-pressurized municipal mains, that hydrostatic force was completely optimized for ancient urban firefighting, allowing crews to project targeted suppression streams directly onto the upper stories of dense Roman apartment complexes, using nothing but pure human leverage. Number 14. Torsion bring Ballista. A wooden bow has a hard physical limit. The energy it can store is capped by how far the wood can flex without breaking. The Romans bypassed that limit entirely. They built a rigid bronze and timber frame and packed it with 2 vertical bundles of twisted animal sinew and horsehair. Rigid bow arms were driven directly into the centre of those skeins. When the bowstring was drawn back with a mechanical winch, it forced the arms inward, twisting the sinew tighter and storing massive amounts of elastic energy in the compressed fibres. Trigger release, the skein snapped back, the bolt fired. In siege configurations, large ballistae could send bolts out to roughly 400 metres on a high arcing trajectory, while delivering devastating, accurate direct fire at much shorter tactical ranges. The bronze caps on the frame were adjustable. Crews could retension each side independently to account for humidity, temperature, and the natural fatigue of the sinew. That's calibrated artillery. In 100 BC, number 13, the Testudo shield matrix. Some of Rome's most advanced engineering wasn't built from metal. It was built from discipline. The Testudo, Latin for tortoise, was a modular kinetic armour system. Under intense missile fire, legionaries closed ranks into a dense rectangular block. The front rank held their large curved rectangular shields, the scutum, forward to form a wall. The flanks angled outward. The interior ranks raised their shields overhead, overlapping them like roof tiles. The curvature of the scutum was part of the engineering. It didn't just absorb impact, it helped deflect it locally, while the overlapping shields eliminated gaps that missiles could exploit. Modern armoured vehicles also use angling and layering to make projectiles glance off rather than punch straight through. But the Testudo achieved a similar kind of protection with wood, leather and iron banding, and a wall of disciplined bodies holding it together. Number 12. The Corvus. First Punic War. Carthage owned the sea. Roman warships were slower, heavier and crewed by men who had never been trained for naval combat. Every conventional engagement ended in disaster. So Roman engineers stopped trying to win at sea. They engineered a way to fight on land, at sea. The Corvus, Latin for crow, was an 11-metre wooden gangplank mounted on a rotating pivot at the bow. A heavy iron spike, shaped like a bird's beak, was suspended beneath the far end. When an enemy ship drew close, the crew dropped the bridge. Gravity drove the iron spike through the enemy deck and locked the two ships together. Legionaries crossed in tight formation and turned a naval battle into the kind of infantry fight Rome could win. Here is the part worth sitting with. The Corvus worked too well. Its weight raised the centre of gravity of Roman warships and made them unstable in heavy seas. In 255 BC, a catastrophic storm wrecked a huge Roman fleet, with ancient sources reporting the loss of hundreds of ships and enormous numbers of men. The added top weight and stability issues associated with the Corvus are widely thought to have worsened their seaworthiness, and the device quietly disappears from later accounts. The weapon was retired. The lesson stayed. Every engineering solution carries a hidden cost. The question is whether you understand the cost before you commit to the design. 4 inventions that prove mechanical advantage beats raw horsepower every time. Number 11. The Polyspastos crane. Trajan's column stands 34 metres tall in central Rome. The capital block at the top weighs 53.3 tonnes. There was no diesel engine, there was no electric winch. There were 4 to 6 men walking inside a wooden wheel. The Polyspastos was a treadwheel crane. The main wheel, the Magna Rota, measured between 2 and 6.5 metres in diameter. Workers walked inside it like a hamster wheel, turning a central drive shaft. The mechanical advantage came from the difference between the radius of the wheel and the radius of the small hoist drum on the same shaft. For a standard setup, a 2.13 metre wheel feeding a 0.15 metre drum, the wheel itself multiplied force by 14 to 1. But that was only the first stage. The rope from the drum then fed into a compound pulley system, the Polyspastos itself, with multi-spool blocks containing 5 to 10 pulleys. That added another 5 to 1. Total mechanical advantage, 70 to 1. 2 workers walking inside the wheel could lift 6,000 kilograms. That is 60 times more efficient than the ramp and sled method the Egyptians used to build the pyramids. Number 10. Ruina Montium. The name translates as wrecking of mountains. That is exactly what it did. In Roman Spain, at a site called Las Medullas, Roman engineers deliberately collapsed entire mountain ranges to extract the gold buried inside them. The setup required years of preparation. Miners hand-carved networks of narrow galleries and shafts deep into the bedrock. Engineers built reservoirs holding up to 18,000 cubic metres of water, filled by aqueducts that ran for miles across high-altitude terrain. Then they opened the gates. Water is nearly non-compressible. When that volume of water raced down into the sealed underground tunnels, it had nowhere to decelerate. The result was the water hammer effect, a massive spike in hydrostatic pressure that fractured the mountain from the inside out. The outer rock face collapsed. The debris washed downstream into channels lined with riffle tables where the gold was collected. 60,000 workers. 6,560 kilograms of gold every year. The same principle, water hammer in a sealed column, is what powers the hydraulic ram pump used on off-grid homesteads today. A falling water column pumps water uphill with no electricity, no fuel, no moving parts beyond two simple valves. The Romans were using that physics to move mountains. Number 9. The heavy-duty bronze ball valve. To regulate the immense hydraulic pressure flowing from their aqueduct links into urban centres, Roman engineers couldn't rely on simple wooden plugs. They invented the plug and ball intake valve. Cast from a robust alloy of copper, lead and tin, these heavy-duty valves featured a cylindrical plug with a precision bored channel running right through the centre. Turn the top lever 90 degrees and the channel perfectly aligned with the pipe, allowing thousands of gallons of high-pressure water to pass through. Turn it back, and the solid metal walls block the flow entirely, creating a watertight seal capable of holding back massive hydrostatic heads. The tolerances between the rotating core and the outer casing were ground so tight by Roman metallurgists that these valves could operate for decades without seizing or leaking under reciprocating loads. It is the exact mechanical architecture utilised in industrial plumbing and high-pressure gas lines today, engineered entirely with manual tools 2,000 years ago. Number 8. Segmented arch geometry. A semicircular arch is stable, but it has a problem. It generates massive outward thrust at its base. To keep the arch from pushing itself apart, the builders had to construct thick, heavy support piers. The Romans found a way around it. Instead of a full half circle, they used a shallow segment of a circle, sometimes on the order of 110 to 113 degrees of curvature. At the bridge near Limera in Turkey, they achieved an unusually low rise compared to the span, producing very flat arches that still carried heavy loads. In a multi-span bridge, the horizontal thrust of each arch pushed against the thrust of its neighbour, cancelling out across the support piers. That meant the piers could be slender. At the Ponte San Lorenzo in Padua, the piers measure just 1/8 of the arch span in width. Then came the second benefit. During seasonal floods, those flat arches and narrow piers offered almost no resistance to the rising water. Debris and current passed through cleanly. 2,000 years later, those bridges are still standing. 4 civic systems that ran an empire of 1 million people, without a single watt of electricity. 4 civic systems that ran an empire of 1 million people, without a single watt of electricity. Number 7. The reverse siphon aqueduct. Roman aqueducts ran on gravity, a continuous gentle slope from source to city. But sometimes the terrain refused to cooperate, a valley too deep to bridge, a gorge too wide to span with a stone arcade. The Romans crossed it anyway. The reverse siphon worked on a principle called communicating vessels. Water in 2 connected columns seeks the same level. The aqueduct fed into a large stone header tank on one side of the valley. From there, the water dropped into parallel high-pressure pipes that ran down the slope, across a low bridge at the bottom called the venter, and back up the opposite side. The weight of the falling water column generated enormous pressure at the bottom of the valley. That pressure drove the water back up to a receiving tank on the far side, set slightly lower than the header tank to keep the flow continuous. At Pergamon, the Madradag Valley siphon dropped 200 metres. The pressure at the bottom of those lead pipes reached 20 atmospheres. That is the same operating pressure as early industrial steam engines. The Romans were doing it with lead, stone and gravity. In 200 BC, number 6, the Groma and the Dioptra. A Roman aqueduct could run for 50 miles and maintain a gradient of less than 0.25%. To put that in plain terms, over the length of a marathon, the water would drop the height of a child. That precision required tools. The Groma was a vertical staff topped with a rotating horizontal crossarm. From each arm, plumb lines were suspended. By sighting along the plumb lines, a surveyor could project straight lines and lay out perfect 90-degree grids. Roman cities were planned with it. The Chorobates was a 20-foot wooden levelling table with plumb lines on each leg and a water-filled trough cut into the top. When wind disturbed the plumb bobs, the surveyor used the water level in the trough to verify horizontal alignment. The Dioptra was the most advanced of the three, a gear-driven, screw-adjusted instrument with graduated circular scales for measuring both horizontal and vertical angles. It is the direct ancestor of the modern theodolite. With these three tools, Roman engineers tunnelled through solid mountain bedrock from both ends and met in the middle. No GPS, no lasers, just optics and geometry. Number 5. The Hypocaust. The Hypocaust was Roman central heating. It worked without electricity, without forced air, and without burning fuel inside the living space. The system started with a prefernium, an external combustion furnace. Wood or clean charcoal burned hot, and the thermal exhaust was systematically routed through a regulated subfloor space supported by short terracotta brick pillars, called pili. From there, the hot gases drew up through hollow clay flues built into the walls, caliducts, and finally exited through the roof. The combustion never touched the air people breathed. The thick concrete and stone flooring absorbed the heat and acted as a thermal battery. That stored energy radiated back into the room as steady, low-temperature infrared, clean, draft-free, no combustion gases, no carbon monoxide in the living space. That is not a small thing. The Romans figured out radiant thermal mass heating 2 millennia before we sold it back to ourselves as a luxury. When the Western Empire fell, the Hypocaust disappeared from Western Europe, but it survived in the Eastern Empire, then travelled the Silk Road into Islamic hammams, and eventually shaped the Gloria heating systems of medieval Castile. The modern equivalent, the rocket mass heater, the masonry stove, works on exactly the same principle. Burn hot. Store the heat in mass. Let it radiate slowly. The honest cost? The Hypocaust required constant manual fuel loading and continuous soot cleaning. It was not maintenance-free. Nothing this efficient ever is. Number 4. The Cloaca Maxima, the greatest sewer. The hydraulic spine of a city of 1 million people, built originally in the 6th century BC and still partially in use today. The Cloaca Maxima ran on no electricity, no pumps, no treatment plants, just gravity and constant volume. Rome's 11 aqueducts delivered a continuous flow of clean water to public fountains, palaces, and the great public baths. The grey water from all of those facilities flowed directly into the sewer network beneath the streets. That constant, high-velocity flow acted as a built-in scouring mechanism, flushing sediment and waste through 1,600 metres of stone and concrete tunnel and out into the Tiber. The system was self-cleaning. It worked because the input never stopped. Modern cities cannot replicate this. Take away the electricity that runs the lift pumps, and a modern sewer backs up within hours. The Roman version, designed 2,500 years ago, would still be flushing. 3 materials so advanced that modern laboratories are reverse engineering them right now. Number 3. High-Alumina fire brick. To build an empire, the Romans needed millions of standardized bricks and roof tiles. Mass production at that scale required something the ancient world had never engineered before: a kiln that could hold extreme heat with minimal fuel. The solution was refractory clay rich in alumina and silica. Both materials have exceptionally high melting points and low thermal conductivity. By selecting clays naturally rich in alumina and silica and firing them hard, Roman kiln builders produced refractory bricks that could withstand very high temperatures without flaking or slumping. The double-walled kiln design with an insulating air gap helped retain heat and reach the high, stable firing temperatures needed for partial vitrification, while using less fuel than a simple single-wall kiln. The heat partially vitrified the clay inside, converting it into a glass-like matrix that resisted water absorption, frost damage, and structural fatigue. That is why Roman roof tiles survive in archaeological sites today, while modern masonry, fired in cheaper kilns, fails in a few decades. Number 2. The Vitruvian water wheel. This is the moment industrial automation actually begins, not in 1760, not in Manchester, in Roman Gaul on a hillside in southern France in the 2nd century AD. The Roman architect Vitruvius described the design in the 1st century BC. A vertical wheel turning on a horizontal axle driven by flowing water striking paddles. But the heavy circular millstones used to grind grain rotated on a vertical axis. The challenge was transferring rotational force at a right angle. The Romans built the Crown-and-Trundle gear, a large wooden gear with projecting pegs mounted on the horizontal water wheel shaft, meshed with a smaller vertical gear connected to the millstone spindle. This was not just a direction change, it was a torque multiplier. The smaller vertical gear rotated faster than the larger horizontal one, increasing the rotational speed of the millstone. Stay with me. At a place called Barbégal, near Arles in southern France, the Romans built 16 overshot water wheels arranged in 2 parallel rows of 8 down a steep hillside. The outflow of the upper pairs drove the wheels below. 16 wheels, 2 parallel mills, 1 continuous water supply. Capacity: 25 tons of flour every day. Enough bread for 40,000 people. That is industrial-scale automation, 1800 years before the Industrial Revolution. Number 1. Self-healing marine concrete. For 2,000 years, material scientists could not explain why Roman harbours, breakwaters and docks remain structurally intact, while modern marine concrete crumbles within 50 to 100 years of saltwater exposure. In January 2023, a team including researchers from MIT and Harvard published a paper in Science Advances that offered a compelling explanation for the extraordinary durability of Roman marine concrete. For centuries, the dominant theory was simple. The Romans used a special volcanic ash, pozzolana, sourced from the Bay of Naples. That was part of the answer. But chemical analysis of Roman concrete also revealed something else: tiny white mineral chunks called limeclasts, distributed throughout the matrix. For decades, modern engineers dismissed the lime class as evidence of sloppy mixing. They were wrong. The Romans were not slaking the lime in water first, as the architect Vitruvius described in his writings. They were mixing dry, highly reactive quicklime directly with volcanic ash at extreme temperatures, then adding water. The reaction was exothermic. It produced intense heat. It accelerated curing, and it embedded brittle lime clasts throughout the finished concrete. Here is the part worth sitting with. When stress cracks form in the concrete over time, the cracks travel preferentially through the brittle lime clasts. Seawater seeps into the crack. It reacts with the exposed lime. The reaction produces a calcium-saturated solution that recrystallizes as calcium carbonate, sealing the crack from within before it can spread. The concrete heals itself, and it gets better. The volcanic pumice in the matrix continues reacting chemically with the surrounding salt water for centuries, growing new mineral deposits that strengthen the concrete with age. Modern concrete weakens with time. Roman concrete grows stronger. The Romans did not build concrete that resisted damage. They built concrete that healed itself. We spent 2,000 years thinking we had improved on it. We hadn't. We had just forgotten how it worked. A company called DMAT is now commercializing this exact chemistry to cut global CO2 emissions from cement production. The cutting edge is pointing backward. Look across all 15 of these inventions and a single pattern emerges. Every one of them is passive. Gravity does the work. Mass stores the energy. Chemistry handles the repair. The Romans didn't build an empire that ran on power. They built one that ran on physics. And when the maintenance finally stopped, the systems didn't fail all at once. Most of them are still here, still working. The cutting edge is pointing backward. Most of what this channel covers works exactly like that. Not forgotten because it failed, but set aside because something else was more profitable. If recovering that kind of knowledge matters to you, click subscribe. The next story is one click away.